So without further ado, I asked Anna to do this because I think this, in my opinion, is one of the most surprising and yet important results in cosmology in many a year, maybe decades, that she's going to be talking about. It wasn't something that we foresaw, but we could have foreseen it. But that's the way it sometimes goes when you make discoveries. So without further ado, Anna, I turn it over to you, and I'll go to mute.
Thanks, Paul. Yeah, so as Paul sent to you already the title of the talk, we will be talking about the cosmological initial conditions problem. Now, it might be a little surprising to many of you that this is an issue worth considering, since broad range of cosmologists nowadays really doesn't consider this issue as being important. Mostly for the reason because, and I believe most would agree with me, because they think that this issue has been addressed to the degree possible, and beyond that, that we know, we cannot really address it. Now, this whole talk will be about disproving this statement. What I'd really like to show you today is that not just that the cosmic initial conditions problem is an important problem, and it wasn't solved in the 80s, it wasn't solved in the 90s, and moreover, it's also not the case that it was solved to the degree that that's possible. And this is really the main message. There is a lot we can do about this problem, and mostly because we have new tools. And this new tool, which will also play a big role throughout the talk, is the tool of relativity, both mathematical and numerical relativity. But let's get to before we jump to the conclusion and to the result, let's just review very briefly what is the conventional picture of smoothing and why one would think that this is the best we can do, this is the best we can get. Now, one should, for completeness, mention, even though today this problem is not being considered as an important one or a relevant one, without this problem, I don't think that the last 40 plus years of cosmological development and successes have been possible. So this is worth really also calling to attention that everything what we know and learned during the last 40 plus years by now in cosmology is due to this problem, due to discovering this problem and addressing this problem. But what is this problem really? Well, first of all, the first approximation is really just as the title said, this is the question, how do we get from fairly general initial conditions, and what this means, this is also something that we will talk about fairly general, to the universe as we observe it today on large scales, namely a universe that is described by extremely simple homogeneous and isotropic geometry that doesn't admit any spatial curvature. That was discovered already in the late 70s, early 80s, that this is not something that would naturally come out of some quantum beginning. And addressing this question led to the idea of inflation, that among others Paul was pioneering, and then to the idea of cosmological perturbation theory, then to the, as Roman knows very well, to the idea of how to measure it, all the series of microwave background measurements that still are ongoing. But really, it's really important, and I cannot stress it enough, this problem is so important because without recognizing the problem, trying to address it, we would be nowhere in cosmology. So that already tells you it's an important problem, don't forget about it. But what was the idea, and why was this idea successful? Why do most people are very happy with where we are now as to how to solve the cosmic initial conditions problem? But the idea was really quite simple, if I may say so. Namely, one looked at the universe as it is today, and one really asked a question, which I will later go to the step 0 question. It's an important question, but this is really not the step, which what we call the last step question. So it was a step 0 question. And one asked, well, if we have a universe that almost looks like ours, what does it mean? Well, if we apply Einstein's theory of general relativity to our universe, namely a universe that's really described by a single dynamical parameter, namely the scale factor, that tells you in an expanding universe, for example, the rate of expansion, it's really the simple, only non-trivial metric component, then we know that the Hamiltonian, the energy conservation equation of relativity, we also call it the Friedman constraint or the first Friedman equation, tells us how the different component of the energy density are related and evolve, with the total energy density. So the total energy density is given by the square of the Hubble parameter, which is defined by the logarithmic time derivative of the scale factor. And we will here throughout work in reduced Planck units, so you don't see here dimensional constant. And then on the right-hand side, you see the matter density, the radiation density, where these are raw matter not and raw radiation not as of some initial densities at some given time. And you can now ask, okay, we know they scale differently. Matter scales as 1 upon AQ, and radiation scales 1 upon A the fourth. And now you can ask it, what are the simplest deviations from this geometry? But the simplest, among the simplest deviation, perhaps the simplest deviation from this flat Friedman-Robertson-Walker geometry, where the energy density is given by radiation ordinary pressureless matter, which scales as just explained. You can add some sort of spatial curvature, zero mode curvature. This is the simplest form of deviation from really gradient freeness, curvature freeness, which scales like 1 upon A square, and K is just a constant, which typically takes 3 values, 0, +1 or -1 for flat, open, and closed. And then you can add some special type of an isotropy. Now, note this component because this will be important. Let's just take it for face value. We add some sort of an isotropy, and this scales as if it was a free scalar field, namely, again, some proportionality constant over A to the 6th. Now, this was the initial idea. How do we introduce a physical mechanism that keeps the good features, namely the Friedman-Robertson-Walkerness, but eliminates in some way spatial curvature and anisotropy? And this was, of course, the idea of that later was known inflation. That one asked, and this will be important without getting into details. The idea was, well, let's assume we have already such a patch, an almost homogeneous and isotropic and flat patch, and a Hubble-sized patch. And the main idea was to ask, what would it take to extend the features of this one Hubble-sized patch at early times, before nucleosynthesis, to a Hubble-sized patch, to many, many Hubble-sized patches, to a patch that entails really exponentially many, we know at the very least e to the 60 Hubble-sized patches. And just to remind you, inflation was the idea to do this by introducing some new energy component, which was then a scalar field. And by keeping the Hubble patch nearly constant, this inflationary field would, so to speak, blow up the physical volume and extend, classically speaking, the features of one volume to the feature of exponentially many volumes. Now, this is not a bad step 0 if you are interested in flattening and smoothing the universe, because it tells you small deviations classically would become smaller. However, and this will be important, this is not really the last step. Why? Because what we said is we don't want to have, it's not a solution to the initial conditions problem to start with a special patch. It's a very special patch. Any relativist would agree with you that nearly flat and nearly isotropic and already homogeneous Hubble-sized patch is something that they would call ultra non-generic, very select initial conditions. So the question is, how do we get there? If we are there, that's good news, then we can do something, namely extend the features of this patch on exponentially many super Hubble scales. But how do we get there? And what's really important here is, and this was really key to the idea of smoothing, you see, it's very important that both for inflation, and we will talk about that in a second, and what was become known due to work to Paul and his collaborators, slow contraction, like pyretic contraction, is that causal connectiveness is absolutely essential for smoothing. You first have to have the right Hubble-sized patch, and what you want to make out of it is causally extending its features over many, many exponential, many Hubble features. Many of you already had a cosmology course. We all know it. Many people call this, therefore, this whole problem, instead of calling it homogeneity, flatness, and isotropy problem, the causal horizon problem, because you want to have a cause. It was thought to be important and maybe even necessary to have a causal mechanism that explains the smoothness, and the smoothness just extends by the time of Big Bang nucleosynthesis over exponential many super Hubble scales. And another component that was important is, so not just that you have to have a very special geometry to start with in order for this mechanism to work, you also need some sort of new ingredient that already has a very special set of features. Namely, it itself has to be already homogeneous. So you fill this Hubble-sized patch with some sort of new form of matter or stress energy that already has to dominate the total energy density. Itself has to be homogeneous. And then it has to drive the evolution. Now, again, if you were wondering that, among all the features that you could have had for the geometry, you have to take this very special non-generic geometry. Now you have to wonder, where does it come from that we can add this other energy component that also already has the right features? It doesn't sound as a real solution, right? And I think this is the greatest concern, if you have it, which just really exposes all the other features of smoothing mechanisms, as known conventionally, that smoothing won't become universal. So the important implication of the causal connectedness that's implied in this classical smoothing mechanism is that only the features, if you don't start with the right patch, you will not get to the right patch. So only select patches will lead to bigger, smooth patches, but everything else that didn't start in this right patch, we just agreed, and this is agreed in all the relativity communities and more broad communities, that it's rare if you don't are lucky enough to start with the right patch. And this is actually the feature that we want to explain. We don't want to be lucky. We want to generically come to that patch. Then you will also remain unsmooth. And this is something that not so long ago, it's not even 2 years, that Mike Turner, one of the scientists who together with Paul established cosmological perturbation theory, and together with late Jim Bardeen, said that this is actually his latest concern related to the conventional picture of smoothing. That smoothing is not universal. This really not just requires select initial conditions. This keeps the final patch that smooths also to be very special. If you're outside of this patch, you don't get smoothed. And this, I think, is the feature that also points towards the idea we have to be able to do better. We want to end up with something that wherever you start, if this mechanism kicks in, smoothing becomes universal. I think if you find such a mechanism, then you should be very satisfied. Then that's a mechanism that you will want to really pursue as the mechanism that explains the logical features of our universe. So keep these 3 features or 4 features in mind, because what I want to show you now in the next, let's say, 40 minutes is that there is a smoothing mechanism that does not require select special initial conditions, that does not require causal connectedness to smoothing, that does not require a stress energy component that's already homogeneous and dominates the energy density at the onset of the smoothing process. And moreover, that leads to a smoothing process that is universal. If I've done that, then we are through with the talk. So we will now leave the expanding universe and start with something that's quite counterintuitive when we talk about smoothing. So most of you think, okay, we live in an expanding universe. The problem of initial conditions is really to explain how between the quantum beginning and, let's say, nucleosynthesis, there's really, if you think in time, almost none. How do you solve this problem? Well, this is to most of you not news now, since you are based in Princeton or interact with this group for a longer time, that maybe the idea that we have to stick to expansion is the wrong idea. Now, that was unfortunately not my idea. And I dare say that it wasn't even just Paul's idea. The idea that contracting universes are incredibly interesting in the context of relativity, but also incredibly counterintuitive, that has really been there since the beginning of GR. If you read the paper of Friedman, he already talks about contracting solutions, the oscillating universe. And if you read papers written 10, 20, 30 years later, you will find that an unusually large number of papers that is occupied with the study of general relativity, in particular as applied to cosmology, is interested in contracting universes. And if you are really good at searching literature, then you will find one of the most important papers written, I think, in the first 50 years on general relativity, and or 60 years in general relativity as in the context of cosmology, is abbreviated as the BKL paper, or the BKL conjecture, standing for Belinsky, Kalatnikov, and Lifshitz. And if you are coming from university where you actually had to learn with Landau and Lifshitz, then you can look up the classical theory of field, and you will see that this paper and the conjecture in this paper is already in the textbook. So this is something that was considered so important in some crises that it even got into Landau and Lifshitz. So what is so important about, and that means something, at least for me, it means something. It's important. It also means that it belongs to our general knowledge about GR. So why were people so interested in contracting universes, and how did it relate to this smoothing question? But the main reason is, I think, is because this is one of the ways you can expose how different general relativity is from Newtonian gravity. And what would you think if I tell you contraction? Now, what you would think is that typically in a contracting universe, gradients grow. Why would you think that? Well, because you think of collapse. You think of matter collapse. When in a locally, you think of contraction, you think of Newtonian matter collapse, you think of messy, things becoming more and more messy, in the sense of more and more gradients are growing, things are becoming more and more inhomogeneous. So you would think, first of all, this is the worst possible idea that one could think of when one wants to explain a universe that becomes gradient-free and isotropy-free and flat, right? That's what people would think, really. But we shouldn't. We shouldn't think this, because contraction in general relativity is very different. And what BKL conjectured already back in the 70s is, late 60s, early 70s, that contraction, relativistic contraction, is not collapse. So the opposite happens as to what you would imagine. Instead of gradients growing, something completely different happens. It's in a relativistic universe that contracts, gradients, and that was the conjecture at some point, and it's also again important. They didn't know when, but that conjecture was at some point, gradients become completely unimportant. So gradients, as the universe keeps contracting and you pump energy density into space-time, gradients will be more and more suppressed so that they eventually don't contribute to the evolution. And completely contrary as to what you would expect, you are not becoming more inhomogeneous, but they conjecture you are becoming, space-time becomes dominated by a very special kind of an isotropy. In a certain sense, a maximally symmetric anisotropy. And it is described by the so-called Kasner geometry. Now you see this geometry is anisotropic, but homogeneous. Right? How do you see it? First of all, it's homogeneous because you see just usually the time component. This is just a particular time parametrization. It's just your -1, as it would be in an ADM, there's a Wiesner slicing, which we will call later ADM slicing. You don't see here 0i components. That means that there is an absence of any type of flux. And you also don't see off-diagonal components in the spatial metric. Moreover, you don't see any spatial dependence in diagonal elements of the spatial metric. However, you see these beta 1, 2, and 3 components, and this tells you that you are not completely isotropic. So there is still an average scale factor, but in different spatial directions, spacetime evolves differently. And these betas tell you at what rate spacetime in that direction evolves or contracts. Typically, 2 directions in this Kasner geometry expand and 1 direction contracts, but it's not remaining constant which directions expand and contract, but switches over time. So you might imagine this is still a mess, but it's a very elegant mess. It's a very homogeneous mess. So it's a relativistic mess, if you wish it. It's a relativistic contracting mess that elegantly is being called a Kasner geometry. And moreover, if one derives the Einstein equations now for this Kasner type geometry and doesn't assume any matter or radiation, you can assume it, but doesn't make much of a difference. Then what you also see is, which I already mentioned, as you might remember, it behaves, these betas behave like a free scalar. So if you derive the Klein-Gordon equations for a free scalar field on a Friedman-Roberts or Walker background that doesn't have a potential, so it's a free scalar, you would get the same equation as you get for the betas. And so they really just contribute to the energy density as if they were the kinetic energy of a free scalar field or three scalar fields. And now if you solve this equation, the right one, then you actually obtain the sigma squared over a to the 6, which, as you might remember, I added to the Friedman equation. So the important part of it is contracting universes are interesting for the following reason. Because it looks like that if you start to broadly generate, so it's without having an idea how it would lead to smoothing, you already should recognize it's interesting, since what is the one element that you want to make vanish? Well, the gradient, the inhomogeneities. And if PKL are right, and this is a conjecture, but we will see that nowadays we have a method to test whether they are right, then you get homogeneity during a contracting universe for free. And that's huge, right? That's huge. And moreover, you get a Friedman-Roberts and Walker universe that's only perturbed by this special kind of anisotropy, which is Kasner anisotropy. So it's a Kasner universe, which is very close to Friedman-Roberts and Walker universe. And why is that huge? Well, if you were back in the 70s or 80s, you would not think it's huge. Because as you might recall, either from what I said, or because you had already a cosmology course, you know that the typical idea of smoothing was go to this almost Friedman-Roberts or Walker geometry. Let's say a Kasner or it's especially curved Kasner, so Kasner that has zero mode curvature, described to the Friedman constraint as I was presenting, where the anisotropy enters as a sigma square over A6 into the Friedman constraint. Then all what you need is some energy density component that will suppress this zero mode curvature and Kasner type anisotropy. Now, why am I saying that people would have thought it was crazy to do that? So on the one hand, it's good news, since you can start from a very broad range of initial conditions, you get a very special geometry. And if you could just get rid of this one element and the zero mode curvature, then you would be done. Then you could start from generic initial conditions and get back to this nice, first to this Kasner geometry, and then afterwards smoothing out the Kasner geometry. And if I'm not completely wrongly informed, this was exactly the idea that Paul and Justin Coore, Neil Turok, and Bert Overwood had when they 20 years ago started to work on this idea that could we get from the Kasner universe to a Friedman-Roberts and Walker universe. And even those who worked on BKL and said you can get to a homogeneous, but only an isotropic universe would have said, no, you cannot. And the reason being the following. Now we start a little bit with imagining what the mess is. The reason being the following. If you really start with the full Einstein equations, and we will get back to that also in more detail, and try to ask if I start from fairly generic, a broad range of initial conditions, and look at the contracting universe where there might be matter or radiation, maybe a free scalar even, but nothing else. No scalar with some special potential, no special stress energy component, just those ingredients that I showed you in the first Friedman equation. Then one can show that you actually get to a Kasner spacetime. And these type of simulations will be very familiar to you in a matter of a few minutes. So let me not explain much. I just want that you have an impression of how it looks. I said it should look like a mess. And I don't think that I promise you too much, because if I run the evolution, and we'll later also explain what the axes are, this is just a space-time, one way of representing what kind of mess it can become if you have an anisotropic Kasner space-time. But this doesn't look, whatever these curves mean, this is definitely not flat and smooth and inhomogeneous, right? It looks like that. The last one, what I said was not right. It's actually homogeneous. We will get back to that why it is, but different points explore different histories. But what you see is this is not, whatever these curves mean, this is not what's simple, what's elegant, what's described by one dynamical parameter. This is a Kasner spacetime. And this Kasner spacetime is not something that would describe a large-scale structure, as we observe it through microwave background measurements, for example. So what was the secret that was discovered in the early 2000s in Princeton, by the way? Well, the secret was that if you combine some ideas from inflation, particle cosmology, with what you know from relativity, then you don't have to be stuck with either only expansion, axis expansion can smooth, or Kasner geometries cannot be smoothed. And this will be now a little boring. So this is a beautiful paper that was led by then graduate student Joel Eriksson that explained, well, there is something that you can do. Now, what was really the problem back in the 70s, 80s, and 90s, people were just didn't talk about it. Why people said, you are stuck with Kasner. Anybody who studied it, you said, you cannot get from Kasner to Friedman, Robertson, Walker. So you cannot get from a very symmetric yet anisotropic universe to a flat Friedman, Robertson, Walker universe. But the problem was that it seemed like that the idea that worked for inflation for an expanding universe might not be working for a contracting universe. Namely, if you introduce a scalar field, a canonical scalar with some sort of potential, or some matter component, whatever that is, that will source you on macroscopic scales a classical energy density component that can be well characterized by an equation of state, which enters the Friedman constraint as an exponent of the scale factor, then you will discover something. Now let's remind us, what does it require to make spatial zero mode curvature and Kasner type anisotropy become irrelevant, and all the other matter, ordinary pressureless matter and radiation, become irrelevant? Now what it requires is an energy density component that sources an equation of macroscopic equation of state that leads to a scaling behavior that dominates the Friedman constraint and for a sufficiently long time. And that would be here. Notice in an expanding universe, all energy density components shrink, right? Because A grows. So matter, radiation, zero mode curvature, anisotropy, and whatever this is shrinks as A grows, right? Because it scales with some power, inverse power of A. However, at different rates. And that's what leads an expanding universe to a flatness problem, because zero mode curvature drops slowest. But in a contracting universe, it leads to an anisotropy problem, because as opposed to the expanding case, everything grows, you pump energy into the whole of space-time. That is, so H is becoming more and more negative, H squared is becoming bigger and bigger. That demonstrates also that relativistic gravity can just borrow energy. The energy is unbounded from below. So you pump energy into space-time, and you pump energy into the individual components. And what you see is, if there is nothing, then what you have to do is, well, what you end up with, and that's why it was not unreasonable what BKL taught, anisotropy will grow fastest, and nothing can catch up with it. And that's why you will be the special anisotropy dominated. Now, what you need to make this energy component grow faster than anything else, you have to have this macroscopic equation of greater than 3. And that's what everybody taught among the relativists. That's impossible, since this would require that the ratio between the pressure and the energy density of this component is constant 1. And why is it the case? Well, because everybody thought that the only thing what you can add there, and it was 70s. This was also in Kip Thorne's thesis, by the way. What they thought is that can only be a fluid. And for fluids, it's true that the macroscopic equation of state is the same as the ratio between that pressure and energy density. And if you had an epsilon greater than 3, that would correspond to a fluid velocity that is supersonic, where the sound speed is greater than 1. And that's not something that relativists wanted to have. And so I said, well, this is not a good, that won't work. Cannot do that. But of course, if you now come from inflation and particle physics, well, we know that there is a energy component that can source an equation of state by its potential energy density. And namely, we know that the ratio, the scalars, a canonical scalar's energy density is just simply the sum of kinetic and potential evaluated here for a homogeneous background. And the pressure is simply the difference between kinetic and potential now. So if you calculate what the macroscopic equation of state is as sourced by a canonical scalar on a homogeneous Cosmology background, then you get that this is just 3 times its kinetic over the kinetic plus potential. Now, why is this important? Well, because obviously all what you need is a negative potential. And recall that in a case of a scalar field, the potential doesn't enter the characteristic of the propagation of the scalar modes, right? Because this is just the Klein-Gordon equation. So box 5 is equal, as we know, just the phi derivative of the potential. The potential sources here, the potential is essential to source the equation of state, but it leaves, and this is really important, the sound speed associated with the scalar unaffected. And even though to us it might sound boring, oh yeah, it's trivial, you have to appreciate that this is something that people didn't believe was possible. Now, putting these 2 things together, as you can read it in Erickson and all, let's taking our an exponential potential, negative exponential potential, which has some characteristic mass scale little m and a prefactor v naught. We know that this actually sources, as a field is rolling down its potential energy density, it sources an equation of state, epsilon, that is exactly 1/2 times the Planck mass over the little mass of the characteristic mass, little m, of the potential squared. And now you can see how easy it is to get epsilon much bigger than 3, right? Think about the characteristic mass scale of the potential would be typical of 0.5 or 0.1. Now for 0.1, you already get an epsilon 50. That's huge. And you haven't done anything. That would be something very natural. If you ask Umron Wafa, this is something that's easily popping out of any consistent quantum theory of gravity. So what people thought, first of all, was not possible for decades in the context of relativity is possible if you source your classical energy density by a scalar. And moreover, this has also been shown, at least to the scaling solution, as just you wish according to the classical picture of smoothing. A scale factor is contracting at a very slow rate. The bigger epsilon, the slower it moves. So physically, not much happening. Think of 2 black holes within 60 folds of contraction. 2 black holes may be distance for an epsilon 50, so characteristic mass scale 0.1, they get maybe to, their distance becomes a third of their original distance. That's nothing. And in the meantime, the Hubble scale shrinks at a crazily fast rate, 8 to the 60, so that's huge. So what did you want? And that was the idea. And this is something that you think, I'm done now with the talk, but it's not true. So it's a beautiful idea. You should be excited about it on the one hand, but only for a few minutes, because I will show you that the idea actually is not working. It's much better, but it's not working like this. It's working in a much better way. But because it's still led, why do I like it? It's not working. Well, you know, if all what you want is step 0, if all what you want is start with this almost Friedman-Robertson-Walker, maybe rely on the fact that BKL is right, and this is actually something where you generically get to, then all what you want is suppressing the little deviation, 0 mode curvature and anisotropy by introducing this canonical scalar with a sufficiently state negative potential. And now what you can see is it leads to an attractor solution where the space-time hardly moves, physical distances hardly move, it contract a little bit, but a Hubble scale shrinks like crazy. So you remember, causal connectedness is given. So you smooth by extending of features, by shrinking, exponentially shrinking the Hubble patch, you causally extend the features of one Hubble patch over exponential many Hubble patches. But you still have the problem, even if BKL were right, even if they were right that actually this geometry is generic, that you are not universally smoothing. Now, what I will show you is not that you are just not universally smoothing, so it's still not good enough. BKL weren't quite right. And what do you need for that to show? Well, first of all, this is a great idea, and that's why it's worth further studying. And that's what I think it's really nice, when you do something new, when you employ a new tool, and we will do that in a second, that you actually think you will just confirm this. You will just confirm, you start with fairly generic initial conditions. Then what you might see is that space-time is going first to Kastner. And then because the scalar field is there and dominates the energy density, however it comes to dominate the energy density, that remains to be seen. If it happens or not, then you will go to flat Friedmann-Robertson-Walker. But I think, physics research is interesting because, or especially in those cases when you think you will show something and you see something completely different, then you know that you actually learned something. And that's what we will do now. So what I said, it's just step 0. I already actually got a little bit ahead of myself. That you start with these geometries, because really what you should start with, once you have seen, okay, I have this mechanism. So first of all, you should never start with what I will be showing you now. Why should you never start with it? Well, because if you cannot solve the easy problem, you will likely not be able to solve the hard problem. So that was not unreasonable. Again, it was actually the smartest way you could go back in the 80s and then later in the context of construction, the early 2000s, to start with, if you are almost Friedmann-Robertson-Walker, can you get to Friedmann-Robertson-Walker? If that doesn't work, I think it's fairly safe to assume you will not be able to go further away from Friedmann-Robertson-Walker, and the same mechanism will get you there. I think, it's quite simple to show that probably you will be, if you're unstable to small perturbations, you're likely unstable to big perturbations too. So this was not a bad way to go. And I would say it was not even a bad way to stop, especially if you were in the 80s or the early 2000s, because that's the best you could do. But it's a very bad way to stop. And here I just want to go back to my initial remark that people think that's the best we can do. Well, it's not anymore. It's a very bad way to stop when you have the tools of solving the full Einstein equations. And we know we have it for about 15 years. So it was around 2007 when Franz Pretorius has completed really long, decade-long research about how to stably mimic the merger of two black holes. And where Franz has not just shown that that's possible, he also gave us the completion of how to use all the sets of tools that were before him developed and led to this discovery, how to put Einstein equations on a computer, that we can study space-time that are way beyond perturbative approximations around exact solutions. So why was it possible, and let's pen back a little bit, to get this far and nevertheless being relativistic? Well, because we are lucky. Because the Friedmann-Robertson-Walker space-time is for most of the time when H is, because H is denoting 3 and 4 curvatures in a Friedmann-Robertson-Walker space-time, it's really in a strong gravity regime. But it's also an exact solution to the Einstein equation, so that the essential curvature, the essential nonlinearity, so the essential non-perturbative deviations from Newtonian gravity is encoded into this extremely simple homogeneous metric component named the scale factor. So if you know that you live in a universe, and we know that given the observations, that actually is described for a long time by this geometry, then you can take it as given. The strong gravity component is given to the exact solution, and then you can perturbation theory around it. That's why, you got so far as we got. On the other hand, we should not stop, because now we can do more. If we know that we can put the Einstein equations in the computer, then we can actually start with nearly arbitrary initial conditions. The only thing what's required from us is that we satisfy the constraint of the Einstein equation, so we don't violate the energy and momentum conservation to our initial conditions. Once we satisfy that, we can really take arbitrary metric and stress energy configurations and test this idea: does negative exponential canonical scalar with a negative exponential in such a space-time, given fairly generic initial conditions where an isotropy dominates, it's inhomogeneous, and the scalar field's energy density is very, very much not dominating, can it lead to our universe? And can it lead to our universe through going first to Kastner? And that's why we should do it now. We could, people with inflation couldn't do it 40 years ago, and Paul and others couldn't do it 20 years ago, but now we can do it. And that's why it's worth paying attention what's happening in other fields that might be relevant to you, because skills and tools that are being discovered here in the context of black hole physics can potentially be incredibly useful in what you are doing and can help you push your own subject forward. And I have already described it, so that's what we will be doing. What we started with was earlier, traditionally, we had to start with the exact solution and perturb it. But now, actually, what we can ask is, what if we start with the full Einstein equation complemented by the stress energy, which is a canonical scalar with a negative exponential potential? Do we get to a Friedman system that's dominated a homogeneous system? First of all anisotropies, all inhomogeneity should vanish. And the energy density should be dominated by the scalar field as evaluated for the homogeneous isotropic and flat Friedman-Robertson-Polka background. And for that, we need numerical relativity, as I just said. And this is not a talk about what to do about numerical relativity. So let me just say really in a few seconds, it's tough. So probably it doesn't really require explanation. Knowing that GR is over 100 years old, we know that a lot of facts about GR have been proven decades later. That was also tough. For example, that for given initial conditions, it admits unique solutions. That's called the well-posedness problem, discovered by Choquet-Bruhat, that itself took almost 40 years. And getting from Einstein to Franz Pretorius and the black hole mergers and knowing how to do it properly took 90 years. So it's hard. I think this is clear that it's hard, right? It's hard because, as I said, on the one hand, the simplest form of the Einstein equations don't work. The computer, we love ADM, we love to slice spacetime into 3+1 and take, so that we imagine spacetime as three-dimensional spatial hypersurfaces evolving in time, where we have the great freedom of threading together the spatial hypersurfaces by simple gauge choices. Namely, most of the time we choose some what we call algebraic gauge conditions. We fix the lapse and we fix the shift. So lapse and shift have we thread together the spatial hypersurfaces. The computer doesn't like it. The math doesn't like it, because it turns out that this formulation, what we so love, what we learned so much for, what we can do in the perturbative so much with, including the marvels of cosmological perturbation theory, again, going back to Jim Bardeen, Paul, and Mike Turner, that's not working if you go on the computer, because this is the one of the few one of the many formulations, actually, where for given initial conditions, these beasts, your 10+ coupled nonlinear partial differential equations don't admit unique solutions. Now, if you are theoretical physicists, we just say, okay, we don't care about spurious solutions. Computer is dumb. The computer will care about everything. And you cannot tell a computer not to care about this, because it turns out that at every point it would pop back. So it's impractical. People tried it actually, but it doesn't work out. The computer is so dumb, it doesn't know, thankfully, what's the difference between a spurious solution and a physical solution. So you just as well can give it the right formulation, because any physical theory that works classically has to get for it. That is the deterministic evolution. We know it has to be. It has been proven about GR. The only problem is it's not pretty. Nobody would want to work with it as a theoretical physicist. We will see why. That's one of the ways why it's hard. The simplest gauge choices, the simplest formulations just don't work. And this is a combination because of the complexity of the Einstein equations, but it's really the consequence of the gauge freedom. And I really just want to call it out now, because many of you work on particle physics. So typically we love a theory that can be associated with symmetries, right? Lorentz symmetry is beautiful. And because we think that we can just take the gauge that fits us best, and the physics will remain invariant. Well, that's in the particle context is fine. But if you go out of the particle context, then the gauge freedom becomes your greatest enemy. Because what it tells you is nothing in the Einstein equations guarantees that your gauge choice will lead to a sensible system that for given initial conditions gives you a unique solution that any deterministic classical theory should do. And so the hunt has to start to find a formulation, a gauge choice, and a representation of the system of partial differential equations that for a given set of initial data gives unique solution, and and that system will also enable you, and here comes both the mathematical combination of the computational challenge, to evolve these equations, integrate the equations without your what we call this is a feature of well-posedness, so admitting unique solutions for given initial conditions and continuously depending, and the solution continuously depending on initial conditions would give. So well-posedness formulation should remain long enough conserved. And the computational challenge beyond that is different problems require different formulations. It's not enough to have a good formulation in terms of well-posedness. You have to be also suitable to the physical situation. And the simplest thing is think about the symmetry of the situations. Two black holes colliding obviously will be a very different situation than a big universe contracting, right? Just a very different situation. If you think about it, if slow contraction should be working, or inflation maybe in some other simulation should be working, simple things like the scale factor evolving at a very different rate, much slower than the Hubble patch, or curvatures, because the Hubble really just represents curvatures. Immediately, anybody who ever solved the differential equation of computer knows that it would immediately lead to a stiffness problem. So from high-level mathematical problems to annoying physical problems, you have to put together everything in just the right way so that you can start with these equations, with the full Einstein equations, and can ask where you get. And, I won't spend the remaining 15 to 20 minutes on explaining what this is, but this is the Einstein equation in an appropriate formulation that you put on the computer. So just for experts, these are gradients, these are anisotropies, these are symmetric and antisymmetric component of the intrinsic curvature tensor, so spatial curvature. This is your scalar. This is the Klein-Gordon equation decomposed into a first order system. And this together builds a hyperbolic system for experts, and is complemented by an elliptic system that tells you how your Hubble normalized lapse evolves. Now, this system turns out to be exactly just what one needs. It's well-posed. It's perfectly well suited for simulating contracting spacetime for a very long time. And it's supplemented by this constraint, by the first one is the generalization of the Friedmann equation. It's a Hamiltonian constraint, momentum constraint, and you have some other constraint connecting simple definitions of components. We use the constraint equation to set the initial conditions. Now, if you look at these equations, I think you appreciate it's not easy. So nobody told you this would work, but using a lot of literature from the past, what people figured, and knowing what you are aiming at, there's a pretty good argument for this system is working. But I have much more interesting result to show than getting into mathematical relativity. I really just wanted to illustrate it's tough. Getting to this equation is a really hard problem. Coding them up is the lesser hard problem. So if you think about computation, and unfortunately, this is not something that it's my idea. It's anybody who works seriously on computation would tell you, especially when it comes to partial differential equations, it's not hard to code. It's hard to know what to code. Once you know what to code, actually it goes pretty quickly. But knowing what to code can take a year plus to work it out. So if you're a computational relativist, you actually do a lot of math and a little coding. And then you enjoy the results of the little coding and lots of math. So this is a two-dimensional example of a contracting universe. After you coded up those equations, so as a result of coding up those equations under fairly generic initial conditions, satisfying the constraints of which are simply just projections of the Einstein equations on your initial spatial hypersurface. And then you can extract from this code how the Hubble normalized energy densities. So for those who are more familiar with the cosmological notation, those capital omegas, so these are the normalized, and you see that they are normalized, as you can see it from the z-axis. They go from, actually should go from -1 to 1, and -1 because potential energy density and the spatial curvature can be negative. So from -1 to 1, they are Hubble normalized, and the x and the y-axis just tells you this is 2 pi times the initial Hubble radius. And it's 2 pi times because we work with periodic boundary conditions. So we have basically twice the initial Hubble size put into this box. That's our universe. We are evolving about 6 times the initial Hubble radius. So 6 times h naught cube volume. And you will see that throughout the simulation. And now if it's truly slowly contracting, then this box will at the end entail, well, the number of EFOs that you can measure here to the cube universes. So it's kind of cool. So what you see here is the evolution of the anisotropy. It's a much more generalized anisotropy than shear. You have the freedom now to put an anisotropy component into every of the 9 components of the spatial metric. And then, so not just on the diagonals, not just the 3 diagonals, but also the off-diagonal elements. We have gradients, which we call spatial curvature. This is, again, not just zero mode curvature, it's all kinds of curvature. And we have the scalar field. And it's really important to appreciate these fluctuations are way beyond the order of 1. You can see it, of course, by eye. So this is very far outside the perturbative regime of relativity, of Friedmann-Robertson-Walker spacetime. And what you see is those who have heard me talk about it already know I tend to call it a really boring simulation for which you can work over a year or two. Well, it's not much, right? Now you see actually what was happening. We are now, it also tells you how stable our code is. We are now evolving 150 folds. So you see e to the 150 Hubble radii, which is e to the 450 Hubble volumes. It's huge. I cannot really imagine it. Try to put it into Mathematica and put an n in front of it. Probably will choke. So it's pretty, right? Now, why do I say it's pretty? Well, because it's exactly how it should look. Do you recall the mass, at least optically, what I showed you? That was a contracting universe before you, starting with generic initial data, almost the same as here. We repeated it actually for the same initial data. And there were all kinds of mass going, and that mass was not vanishing. And what you see here is not a mess. So that's already good. But what you moreover see, everything is homogeneous. So that's a good news. The scalar field, so blue dominates the energy density. So the scalar field come to become homogeneous, didn't start out homogeneous, come to dominate the energy density, didn't start out to dominate the energy density. And both the curvature and anisotropy are at 0. They don't contribute to the energy density. And you saw it was very quick. So that already is something that you could never conjecture. BKR didn't know how quickly it would go. And they would have told that this is possible. But did you see if it was different from what Paul and companions said? Did you see if it went through Kasner and then to Friedmann-Robertson-Walker or not? Well, I didn't see it either, but I know it didn't. And I slow it now down a little bit and then try to imagine what it would mean that it goes first to Kasner. Since they are remote, I tell you what it would look like. It would look like that if it's really Kasner, then you get 3 homogeneous sheets. The red one would be at 0, but the blue one would be somewhere below 1, and also below the homogeneous green sheet, because that would mean that you have a homogeneous anisotropy dominating the scalar. And if you saw that, then you are at Kasner. So then BKR were right, and it was reasonable for Paul and his collaborators to assume that they went from generic initial data to Kasner, and then we would have to see that the 2 sheets switch. This is 25 times slowed down the initial simulation. You see, we are only at 2 E folds now. And does it look like anything like the 2 sheets? The right answer is not, right? So there were little bumps in the curvature. You didn't really know how it looks because the scalar field kind of went at a certain point up to dominate. Still something, it is just resolution, so that is not actually, it's just already a finished simulation. So that doesn't mean right now anything that it's a little bit noisy. The blue went up, but there were some DAS, and if you really watched well, then there were some little curvature components also there. So it was certainly not the case that, and I can show that to you. If you go back, you see those little dells in the curvature? So it wasn't the case that first the curvature goes down, and then the shear comes up, and there is somewhere in between the scalar field. Now, is it just because of the simulation? Because we chose some special initial conditions? Or is there something wrong with the original explanation? So we like the outcome, but it doesn't seem to fit with the original explanation. What does one do now? Sort of, it's okay. That one does this has numerical relativity, such a simulation in 2D. I should explain it's 2D, but it's 3D. So what really you see is we, of course, evolved the 3 + 1 dimensional Einstein equation. So if your guess was, oh, something is wrong here because it's just 2D, no, we evolved the 3 + 1 dimensional Einstein equations, but we only align homogeneities into 2 spatial direction. Now you can do it into 3 spatial direction. It turns out nothing changes. So the first thing what you do is you do it with lots of initial data and see if this is something that's typical, right? You cannot do it. You have the toy. You work hard enough to have this coded up, so now you have the toy, and once you do it, you will see this is typical. And the reason for that is because nobody got it completely right. And that's why it's cool to have a new tool and employ it to an old problem. That, I think, is one of the probably keys of finding something new. When you look at something that people don't understood, but with something new, and you get some surprises. And so what you see here is actually a smoothing mechanism. And even if you hadn't seen it, it's not working as people imagined it. And then people I name here, Paul, Justin, Bird, Neil, and others who worked on these issues. It's much better. It's much better because it doesn't work as anybody thought it would work. And in order to demonstrate what it means that it doesn't work, let's get back to what I started with, namely the BKL idea, the idea that gradients in a relativistic spacetime that contracts would become very quickly irrelevant and don't contribute to the evolution. What I reminded you was that even though they thought it was reasonable to assume it, actually for the same reason why we could eliminate, I explained you why people thought flatness is an expanding universal problem or zero mode curvature. Because of the scaling behavior, they thought curvature goes, the leading order curvature goes like 1/a square. The leading order anisotropy goes like 1/a6. So for inhomogeneities will be quick, not quickly, they didn't know actually, they wanted to know at some point and root to the singularity will be suppressed. And what dominates is the anisotropy, the special type of anisotropy. But they didn't know how quickly. And it turns out they also didn't have, and not even at early 2000, they didn't have a means to checking it. But when you check it, then you can check it how quickly it goes and how it goes. So how quickly do gradients become unimportant? And do they really become unimportant in a way that any curvature components, including zero mode curvature, have to quicker vanish than anisotropy, homogeneous anisotropy? And the answer is, I give it away, they go away very quickly. It would have been a huge surprise, I believe, for BKR. They thought it happens only in the vicinity of the singularity when you are close to the quantum gravity scale, or classically even below it. But it turns out it happens within order 1 forwards. That's huge. That's huge because that means that you really can generically solve the inhomogeneity problem. But it means a lot more. So how do you do this? So again, nobody has done it before. Who has this idea of how do you study it? Well, one thing doesn't work is pencil and paper. The equations are beasts, and that's why you didn't have access to it. But the code can do everything for you. So, most of the time when you hear simulations, people just show you the movies, and the movie is the end result. So when especially if you go to AstroTalk, they show you incredibly difficult to update supercomputer simulations, very expensive, look very impressive, and that's the result very often. And numerical relativity, the last thing that the endpoint is your simulation. You see, we also don't spend too much time on making them pretty pictures. Obviously, I think you all know that the beautiful movies that you see are not simulations that astrophysicists do, but illustrations of simulations. So they employ usually visual artists who do then the simulation. So never get fooled by that. But in relativity, that's not what you care about. You might care about if you go to some press conference and want to go to a granting agency and want to present your results to people who, when you have 5 minutes to show how cool your results are. But if you're a scientist, really, what relativistic equations give you is curves, right? Gravitational waves are curves. That's what we're interested in. Solving the binary black hole merger was getting the right waveform. What do people look for when in LIGO data? Well, the matching waveforms. And here we also get curves, and two-dimensional curves are, of course, sheets, right? Very interesting topology sheets, I mean, curved, but that is what we get, right? And that's what we care about. And then we don't want to stop here, but what we also want to ask is, now what can we do as with the simulation and things and results? Where the simulation, just remember, it solves the equation. So I decide what I want to see. So if I ask when the gradients become unimportant, I can just take, and if I want to ask if curvature decreases, then I can just take a curvature component. Here it is, as is just NAB are just simply components of the extrinsic curvature or spatial curvature. Is that was scalar? So I can just pick one component. Here I will take and show you one component and see how it evolves. So again, you take the same box as we had. It is again normalized. I can Hubble normalize my curvature too so that it fits into a neat box and just see what it does. Why not? So obviously it's not smoothing quickly, right? It starts to play around and oops, now it goes to 0, around 18 e-folds. Now, if you had really good eye, or if I tell you what to look for, then you would still not see it. The only thing what you saw, it started to grow, and at some point in some weird way vanished. But before it vanished, it was never a sheet. So that already tells you it wasn't exactly whatever's happening, it's not going to some Kasner type spacetime. And this is typical. You can do it for almost all initial data, this will happen. But you can do more. If you want to say, how quickly do gradients vanish? Is it really happening that those initial bumps get stretched and grow because the gradients grow, or something else is happening? But then you just take the gradient components of the equations. Gradients are spatial partial derivatives. So you can just print them, right? You have a code, the code does exactly and does print exactly what you ask it to print. And then you can just say, now first we printed all the right-hand side, and now we can just print the gradient terms. Look at this. Oh, this is not growing. This is pretty impressive, right? It's not doing anything. I mean, except for vanishing. And now if I take you screenshots at the 0th, 5th, 10th, and 30th e-folds, and here are all the terms, and here are only the gradients, then this is actually what BKL would have loved to see, because on the one hand they were right, on the other hand they were completely wrong, because it was incredibly quick. And it was not that the curvature vanished first. You see the curvature starts to grow, but by initially the curvature is being gradient dominated. You see the two are almost the same. So you started with initial data that was incredibly inhomogeneous, and the spatial curvature was dominated by the gradient terms. What happened is that the growth was due to the homogeneous curvature terms, and the gradient immediately started to drop. So two things really important. The one is the curvature doesn't start to drop immediately. It actually starts to make some funny business and really drops, around 20 to 30 e-folds, while the gradients drop very quickly. So this turns out to be really important, because now this is something that you have to swallow, because you have all been, except for those of you who haven't yet had a cosmology course. So I think it's Maxime is the only one who hasn't yet been indoctrinated. The smoothing has to be causal, right? Can only be that all the initial conditions are related, problem are related to the fact how we get from one right kind of patch to many, many patches by starting with that patch and extending by causal means the features of that patch to another. So first smoothing, then super Hubble smoothing. Now, if you look at this, that says it's not true in contraction, not just does not go to Kasner, it's not just, it doesn't go first to a smooth patch. And that's really important when you, how do I know it? Now you have to ask is, what is she talking about? How do I know this? Now, well, what do gradients mean? Just think about it. Gradients mean that different patches communicate, different points of space-time communicate with one another, right? If I suppress, if the gradients dynamically get suppressed, that they don't contribute, that means that eventually, and very quickly, actually, not just eventually, after between 5 to 10 e-folds, space-time points don't communicate anymore to one another. But at that point, they are still messy. I mean, look at that. This is not smooth. There's even curvature. And if I added you anisotropy, that would be even worse. So however smoothing is happening, this is not causal. It's quite the opposite. And this is extremely interesting. Because now you know it can be universal. Because if smoothing is causal, and I think that this is one of the reasons why we never got beyond the existing paradigms, if smoothing is causal, it cannot be universal, right? You first need a Hubble-sized patch, but we know it's extremely non-generic, and only those regions that are causally related to this original patch will become smooth. But if you have a space-time that evolves in an ultralocal way, then it nevertheless smooths. Then you know on the one hand that the smoothing has to be universal because ultralocality is quick. Space-time points very quickly don't communicate, and that happens before you had a chance to smooth. So if you will have to have a chance to smooth, and obviously you have, and actually mathematically we can even prove that you have once you are ultralocal, given the negative potential for the scalar, then it has to go everywhere. It turns out you get either everything or nothing. If you smooth through ultralocality, then you can only smooth if every point goes to the flat Friedmann-Robertson-Walker solution. And that's huge. So what turns out is that ultralocality is, first of all, defying the idea that smoothing has to be causal. And moreover, it tells you that if smoothing ought to be universal, it cannot be causal. And this all because, and we can learn all this because we have numerical relativity. Because we can really run the simulation and ask, was this really, is this really working as, almost 100 years of research taught to be working, but only having pencil and paper and thinking? And the answer is no, it's much better. It's much more interesting. But this process of going from gradient dominated to ultralocal, this is very nonlinear. You cannot do it by pencil and paper. It's very non-perturbative. So the only way how you can do it is computation, but not dull computation where you just stop, okay, that's the result. But you actually analyze the result by doing lots of examples. And this is a little bit like Roman does in the lab, but we can call it numerical experiments. So we can repeat it again and again for different initial conditions. And it is a little bit like as if we had as many universes as if we want to have. We can run actually the movie as often as we wish, and we have computer time. I should also mention it's very nice because these simulations, 2D simulations, last about half an hour to an hour. So it goes very quickly. And if you do it in one day, which is a very good, just for discovery, that goes in a matter of a minute or less. So it's really cool to do numerical relativity in the context of cosmology, because, if you have talked to colleagues who work on black hole simulations, that goes into days and weeks, sometimes even months. One simulation comes out, depending on your complexity of matter content. Okay, but let's get back to what I said. So what we did is, ultralocality, just know it is quick. And somehow the points, and this is just a different representation, what you can make with the code. So first of all, we concluded it's quick and it's true. And what it leads to is that very quickly, space-time becomes almost everywhere causally disconnected. And thanks to the presence of the canonical scale with a negative potential, every space-time point seems to know where to go. And this is a representation of that. Now we follow, because that's also something you can do with relativity. I have first been showing you the entire box evolving and the total energy densities and total shear density and total curvature density. Now, but you can also pick off a space-time point, or here we picked off 6 space-time points, and you can follow them individually. This is just a very convenient way of following certain points in time. So the color coding tells you where a given space-time format at E equals 0, 5, 10, 15, 20, and 25. They start out, and this is like a parameter in a particular, we call it sigma or orbit plane, the particular parametrization of the anisotropies. What's important for it is the circle would be your Kasner circle. So you would have it beaky over, right? And first, all points should have been going on the Kasner circle straight there, and then somehow shoot into a radius into the middle of the point, which is flat Friedmann-Robertson-Walker, in the middle of the circle. The middle of the circle is flat Friedmann-Robertson-Walker. The circle is itself the Kasner solution. And so the idea was you could see what would happen if BKL were right, then the points would just go on a radius to the middle of the circle. But it's not true. That would be the sheet, so what I explained you how it would look like. But it's not happening. What's happening actually is that different points, some start outside the circle, some start inside. So this is just depending on your initial data, how it's distributed over your initial hypersurface. And what you see is they explore quite different paths. They don't all follow the same paths. The only thing what's common about them, they don't even take the same time. Some is there within less than 10 e-fold. Some take much longer than 10 e-fold. So what you see is, and they explore very individual paths. The only common thing that they have is that first you can show that they become ultralocal. So they ultralocally evolve. By the way, that's representing it too. The fact, the fact, so we took the simulation, the same simulation that I've shown you. We know that around from e-fold 5, the evolution is ultralocal. So these points actually don't communicate with one another. The reason that they get to the circle is for each individual point given. They don't get to the circle, they don't get to flat F4W because they are communicating with one another. It's not a causal evolution. They get there because, and we can show that, that's where I get to in my last slide. So we are almost done. Because that's the only fixed point for most initial conditions where they can get, only stable fixed point. And that's pretty cool. So the reason is not that somehow you first go to Kasner, then you add magically this homogeneous scalar field that dominates the energy density, and then that suppresses the individual component. That's all wrong. The right component is you need this scalar field with a sufficiently steep negative exponential. But why you smooth this is a combination of ultralocality and dynamical systems evolution. Namely, what you do is the system first becomes ultralocal, and these really complicated equations, which were coupled nonlinear and partial differential equations, all in some sense lose their gradient contributions. So, and this is physical, so the inhomogeneities don't play any role. Points don't communicate with one another, and every single point follow the same ordinary differential is described in evolution as following an ordinary system, ordinary differential equation system. And that system turns out has only two fixed points, and the one has a huge basin of attraction. Basin of attraction means all the initial conditions, all the points that eventually end up at the fixed point, the flat free body Robertson-Walker, and one with a tiny basin of attraction that's so insensitive to perturbation of the initial data that never gets there. Now you might guess which one has the huge basin of attraction. That's the flat Friedman Robertson-Walker. And the beautiful thing about relativity is you can prove it. Now you can go back. Now, if you are a theorist who not just like computation, but loves to work with pencil and paper, you use your simulations to establish ultralocality, establish that ultralocality is fast, and also understand that it's not working to first going to Kasner and then to Friedman-Robertson-Walker. And now you really want to understand why an ultralocal system directly goes to flat Friedman-Robertson-Walker. But then you do what we call in physics dynamical systems analysis. Just simply ask, what are the fixed points, the stationary points of the system, point solutions of the system? And then you ask, again, back to numerical relativity. Now you really study thousands of configurations of initial data, and you try to numerically establish how big is the basin of attraction of those fixed points. And now, how do you do this? I'm saying numerically established. Well, the best way of establishing, first of all, that Kasner is something that's extremely delicate, that most initial points won't go there, is start with almost Kasner and poke a little bit. Now, you already know how Kasner should look like, right? Okay, so sorry, just the color coding is, so you have matter still, right? You have matter, which is still blue. Then you have curvature, which is red. And you have an isotropy, which is, it looks a little black, but it's still green. And this is the sheet that I said. This is exactly a Kasner spacetime, almost exactly, right? Homogeneous and isotropy dominated, there being almost no curvature. and then you have a scalar field energy density that compensates, that is very little kinetic energy of the scalar, and mostly you can see the potential energy density is more because it goes negative. Now, if you poke the system, but the original idea was Kasner stays Kasner, because the scalar field energy density node by far doesn't dominate the energy density. So this solution should never go to flat FRW. Now I tell you, it's not exactly Kasner. It's like almost as Kasner as it gets, but one off diagonal, we added on one off diagonal of the spatial. If you remember, Kasner would be the only diagonal element of the spatial metric. No off diagonal elements anywhere. Diagonal components are homogeneous. Now we have the Kasner diagonal components, but on 2 points, because the spatial metric tensor should also be symmetric, of course, we are in GR, we added tiny perturbations, a constant 0.01 Hubble normalized perturbations. And now look at the effect. Well, it looks like as if it was just going to another Kasner, right? Still, it's where we are already 14 E4. It doesn't look that good. And now magic happens, right? So something happened. It's not clear what. I can tell you what. The Kasner solution is so unstable, even to small deviations. And the basin of attraction of Friedman-Roberts and Walker is so big that what you saw is exactly that. If you poke Kasner a little bit, even though the energy density would look like as if they were just going from one Kasner to a little bit of another Kasner, if I'm, but short of time, I don't have time to it, if I showed you the individual curvature component, in the background, they are going crazy. What's happening actually, what you thought, and this is beautiful again, what you thought was totally irrelevant is homogeneous spatial curvature. You remember earlier one thought, the people, Erickson et al., Poe and collaborators thought that curvature becomes unimportant very quickly. That's not true. Once you want to understand what's happening here, and you plot the evolution of the individual spatial curvature component, those NABs that I showed you, but turns out that they are, together with the scalar field, kinetic energy, they are absolutely essential to destabilize the Kasner solutions. So not just that they become irrelevant, the gradient become irrelevant, that's true, but the homogeneous curvature components are there as long as an isotropy is there. And what they do is they, together with the scalar, destabilize the Kasner solution and lead to the only other possible fixed point, the flat FRW solution. And now you want to also show what is the basin of attraction of the Friedman-Roberts and Walker solution, which is spatially flat. And now this is, every time when we have the right solution, it's boring, but it's boring in a good sense. Now, every point in this phase spot corresponds to a whole set of initial data, initial conditions. But it turns out that the most important initial conditions is the average field velocity that decides almost everything. So you can have whooping anisotropy, whooping inhomogeneities, curvature in all direction. The scalar field can be really almost arbitrarily subdominant and messy. What's important is what is the average. So locally, the field can go uphill, downhill, the potential energy density. But the average velocity of the field will determine if, despite of all the mess in the geometry, which puts you very far outside the perturbative regime of Friedman-Roberts and Walker, you will smooth. It turns out that already if you are at rest, and for, as some of you also knew him, as I showed with Timo Kist for more generic potential, so we had first shown it for exponential only, but you can ask it, does it depend on the potential? No, it only depends really on the macroscopic equation of state at the potential sources. So this is coming from our May paper, just appeared a few months ago, and confirming and extending the results of earlier papers. That tells you that the only thing what matters is what equation of state, what is the characteristics mass scale of the potential, because that will correspond to a particular equation of state, epsilon, you see, and the initial average velocity of the field. So locally, the field will be whooping, going uphill, downhill, and so on, but there is an average velocity. And if that's 0, and in Hubble radius, it can be very small, but the field should not be an average move uphill. In some cases, we have shown actually is also possible, but generically, the only requirement is, and it's classically, of course, in a contracting universe, almost a triviality, that you won't have a scalar field shooting uphill. In a cyclic universe, if you just came from a, let's say, dark energy domination, it would of course be trivial. So it's a very, very mild restriction. And notice also that this is not in Planck units, the velocity. It's in units of the initial Hubble parameter, which is tiny since the contracting universe starts at a very low energy density. So you can see it that everything what's white, and really the right scale is this, goes to flat Friedmann-Robertson Walker. And some points go here to mixed state where some regions are Kasner. And there are some features for experts who have thought about it. This little region goes through spikes, which are tiny little interesting relativistic features to FRW. And this is just a mixed state, which is most of the proper volume is FRW, and some of the proper very tiny regions are Kasner. And it's also very important in no case does the space-time, except when you start almost exactly at Kasner, really exactly at Kasner, goes to Kasner. So even in cases where there are tiny proper volumes that are Kasner, the overwhelming majority of space-time is flat Friedmann-Robertson Walker. And all that was reached, not because you had the right initial patch, it was reached because relativistic contraction is fundamentally ultralocal. And therefore, if you smooth, and that's what's happening, is you have to smooth everywhere. And this is where I'm going to stop, just summarize it. I told you, once I'm through with refuting all the initial assumptions, what's necessary for smoothing, I'm done with the talk. What did we say? Well, we said, and people think this problem is not so important because the best what we can do is start with an almost right patch and causally extend the features of those patch on super Hubble scales and exponentially many super Hubble scales. And what I said, that's at best step 0, because what you really need is non-generic initial conditions. We have it. And I also said that it's important that we smooth because that we are ultralocal, because if you want to have universal smoothing, you can only have universal smoothing if you are not causal. And ultralocality guarantees you ultralocality, meaning that we are not going from generic state to Kasner, then to Friedmann-Robertson Walker, as the perturbative analytic picture would say, but we evolved through ultralocal evolution to a Friedmann-Robertson Walker state, where because ultralocality is settling in very quickly, the evolution is fundamentally non-causal and therefore universal. And more importantly, we don't need some magic where the scalar field energy density dominates. And therefore, we also don't need all the specialty added to the initial assumption of a Hubble patch. And so we end up with universal smoothing. And also that's, I think, is a good place to stop. And then I ask a question.